Hello everyone, welcome to my YouTube channel S3 Chemistry Lectures. In this video, I'll be explaining the entire experiment of qualitative organic analysis, in which I'll be explaining in detail about each of the steps from starting with preliminary examination, then with the determination of physical constants, detection of elements, solubility test, and even how to find out the various functional groups, the various tests that need to be performed, along with the positive as well as the negative results of each of them, and also how to prepare the derivatives for the organic compound that is given to you. So this particular video will serve as a complete guide for all the tests that are required to be performed under qualitative organic analysis. So let us start with understanding the preliminary test. So first of all, in the preliminary test, we are going to identify certain characteristics and we are going to look into those characteristics in the given organic compound. Based on this, we can have a rough idea about what may be the given compound based on certain assumptions. Okay, so let us start with the physical state. So first thing, you need to observe whether the compound is a solid or a liquid. So suppose if it is solid, then the given compound may be resorcinol, glucose, urea, benzoic acid, salicylic acid, or benzamide. Suppose if it is a liquid. So before that, about solid, here I have given the pictures of the various compounds. So most of the solids that are given to you will be white in color. So it is quite difficult to find out which compound has been given. But the resorcinol, although it is in the solid state at room temperature, you can identify that the given compound is resorcinol because of its color. It is pink in color, whereas the other solids that will be given will be white in color. So with just physical state examination, it is not possible for us to decide or predict what is the given organic compound. Suppose if the given compound is liquid, then it can be aniline, benzaldehyde, acetophenone, benzyl alcohol, ethyl benzoate, chlorobenzene, or nitrobenzene. Now, from this, what we can understand is based on the liquid and the solid compounds. So as we already know which are the compounds that are present in the solid state at room temperature and the ones which are present in the liquid state at room temperature, we can easily rule out the ones. So suppose you've got liquid, so you can easily rule out the other compounds which are in the solid state at room temperature. So you'll have only a few options left in order to identify the given unknown organic compound. So this is how the preliminary examination gives you a rough idea about what may be the given compound. So here the first clue about the identity of the compound is obtained just by looking at the physical state. Coming on to the color, so next we are going to observe the color of the sample. So as I already told, for resorcinol, although it is in the solid state, it is possible for us to identify that the given compound is resorcinol just by looking at its color. So if it is pink, we are easily identifying the given compound as resorcinol. Suppose you have got a liquid sample. Now, if it is brown in color, then it may be aniline. If it is yellow, then the given compound may be nitrobenzene. And as I already told, most of the other solids, those are given as the samples for the organic analysis, those will be white in color. So here, mainly based on the color, it helps us in preliminary identification of the compounds. So especially you can identify the resorcinol, nitrobenzene, as well as aniline by making use of this particular test, preliminary test, in which you're observing the color of the given compound. Next is with respect to the odor. So this is also a very important preliminary test. And here, if you are good enough in identifying certain odors, the characteristic odor of certain compounds, then here itself you can identify a few compounds. Especially if I'm talking about benzaldehyde, it has a specific bitter almond smell. So when you check the odor of the compound, especially here, care has to be taken. It has to be done by wafting technique. So I'll be showing how it is done with the help of pictures. So here we are not going to inhale the vapors directly. We are using the wafting technique in order to check the odor of the given unknown organic compound. So suppose if the compound has the bitter almond smell, if the sample has a bitter almond smell, then we can say that it may be benzaldehyde, which is given to you. Suppose if the given organic compound has fishy smell, then the compound may be aniline. Pleasant odor, if the compound is giving the pleasant odor, then the given sample may be ester. ketone, or alcohol. And most of the solids except naphthalene, most of the others will be odorless. So suppose if you've got liquid samples, if it is pleasant, then you have three options. It may be esters, ketones, or alcohols. And fishy odor as well as bitter almond smell will give you a clear picture about what may be the given compound. Suppose if you have got the liquid sample. Here, as I've already told, precaution, you should never inhale the given compound, the given sample directly, and always we need to use the wafting technique. So this is how it is done. So suppose you've got aniline. Okay, so this is how it has to be done. So you're going to take the sample, you're going to take it in the test tube. So this is how it is given to you in the exam. It is given in the test tube. So it will not be told to you. So what is the compound? So what we need to do is we need to take only the vapors. We have to just smell the vapors with the help of our hand. So you have to maintain the safe distance here, right? And you have to check the odor of the vapors. And just by using your hands, you're just taking the smell of the vapors, and then you're going to the perception. You're going to check the odor. Okay, so based on that, suppose if the smell is fish-like, okay, the fishy odor, if it is present, then we say that we can guess that the given compound may be aniline. Okay, so next is Bayer's test. This is also a very important preliminary test. So here we are going to identify if the given compound has saturation or unsaturation. Right. So mainly if the unsaturated compounds have been given to you, they decolorize the alkaline potassium permanganate, whatever is added, the reagent that is added during this test. So if there is decolorization, that is the positive result in this particular Bayer's test. So based on that, you can easily identify that the given sample is having unsaturation. So experiment is very simple. You're going to take the substance in the test tube, add sodium carbonate solution and 1 drop of potassium permanganate solution. So mainly here we are maintaining the alkaline potassium permanganate, and then you're going to shake the contents of the test tube very well. So suppose if there is decolorization, then we say that the given compound has unsaturation, and this is the positive result for the Bayer's test. So here there is discharge of the pink color, which gives you an idea that the given compound has unsaturation, or it may be a reactive compound. If there is no discharge of the pink color, then the given compound is saturated compound. So this is what the reaction takes place when you're going to add alkaline KMnO4 to the given organic sample. So the compound, it reacts with alkaline KMnO4. So in the presence of this oxidizing agent, that is alkaline KMnO4, it is converted, the compound is converted into the oxidized product. Along with that, MnO2 is produced, which is brown in color. So because of that, in this picture, you can see that there is brown coloration because of the formation of MnO2. Now here, mainly the positive test is the pink color has to be disappeared, or it has to be discharged. So only then we say that the Bayer's test is positive. Next, coming on to the ignition test, very, very important test. And with this particular preliminary test, you can identify so many different compounds, and you can have a clear picture about especially two different compounds, that is glucose as well as urea. So let us look into how to perform this experiment. So you need to take a small quantity of this substance on a spatula, and then directly you're going to hold the spatula in the flame. So you're going to ignite the sample in the flame. So suppose if the particular compound, the sample, it burns with a sooty flame. So you can see that much of the smoke is produced. So sooty flame is produced. Then we can say that the sample is aromatic in nature. Suppose if a non-sooty flame is produced when you're performing the ignition test, so then we say it is aliphatic compound. Now, there is also another way. These are the two other observations which helps you in identifying the two important compounds. Suppose if you have been given glucose or urea, here itself in the ignition test, you can get a clear idea about what is the given compound. Right. So suppose if the substance charts and a black residue is left behind, you can see in this picture, a black residue is left behind. So in such case, we can say that the given compound may be sugar. So glucose is one of the samples which may be given for qualitative analysis. So suppose when you do the ignition test, then you get this black residue that is left behind on the spatula, then you can have a clear idea that the given compound may be glucose. Suppose if the compound burns with the white residue, then the given compound may be urea. So with this, you can, especially using this ignition test, you can get a clear idea about the glucose or the urea that may be given to you, as well as you can differentiate the given compound as aromatic or aliphatic in nature. Next, talking about the Bilstein's test, which is also called as the copper wire test. So here, mainly it helps us in detecting halogen-containing compounds. So procedure is very simple. First, you need to heat the copper wire until it is clean, because mainly, suppose if there are any impurities or any other unwanted content that is present on the copper wire, so that has to be removed off. Otherwise, there will be no copper oxide that is formed. Okay, so here mainly we require the copper oxide, which has to react with the halogen compound to give the green color. Okay, so that's why we are going to heat the copper wire first. After heating, then we are going to dip this copper wire in the compound. So suppose you have a liquid sample. So we may be thinking it may be chlorobenzene. So what you have to do, you have to dip it in the compound, and then you're going to reintroduce this copper wire into the flame. Suppose you get a green edged flame, then the given compound is halogenated hydrocarbon. Or there is one more thing that you need to keep in mind. In this case, even urea also produces a green edged flame. So I'll be just adding one simple trick here. Suppose you get urea, okay, as an unknown organic compound for analysis. So let us say you're going to do the ignition test. You're getting a white residue after the ignition test is done. So you'll be having an idea that the given compound may be urea. Now, when you perform this Bilstein's copper wire test, again you observe a green edged flame. By now, it should be almost sure that the given compound is urea. So you can directly go for the test for urea in order for confirmation, so that the time that is required for analysis will be reduced drastically. Okay, so this is with respect to the Bilstein's copper wire test. So green edged flame has to be produced. So if green edged flame is produced, then the given compound is halogenated hydrocarbon. So especially the chlorobenzene will be the one that is given to you for analysis. So we can say that chlorobenzene may be the compound that has been given. Okay. So mainly, as I already told here, copper, first it should react with oxygen in the air. So especially you're going to heat it, right? You're going to heat the copper wire so that you're going to get copper oxide. Right? So first thing, we need this copper oxide. So I told you, right? Only if this copper oxide is present, then only it can react with the halogenated compound to give the green edged flame. So here, the halogen compound, it reacts with this copper oxide to give copper halide. Okay, this copper halide is especially volatile. So because of which you can see the green edged flame. So here mainly the copper halide that is formed, it imparts the green color to the edge of the flame. Right. So next is determination of physical constant. So this is the second step that we need to go about during the qualitative organic analysis. The first step is preliminary test, under which we have mainly discussed about the physical state, color, odor, Bayes test, as well as ignition test and the copper wire test. So all those tests have to be done, and the observations that have been observed have to be recorded very neatly, so that you will get an idea about the general idea about what may be the compound. The second step is determination of the physical constants. That is mainly you're looking into the melting point as well as the boiling point of the given sample. So suppose if a solid is given to you, you're going to check the melting point of that solid. And with the melting point data, it is easy to identify what may be the given solid. Suppose if it is a liquid, then you're going to check the boiling point of the given liquid, and you're going to report the value as observed boiling point plus 3% correction. So this particular percentage correction is based on the altitude. So I have explained all this in detail about how to find the melting point as well as how to find the boiling point of the given sample. And the link to these videos have been pasted in the description box. You can go through that to find out the method for determining the melting and the boiling points of these samples. So this is the particular chart of the boiling point as well as the melting point of the various samples that may be given. So you can take a note of these boiling points as well as the melting points, that is the physical constants of these different compounds. So for resorcinol, it is a solid. So we have the melting point 110 degrees Celsius. So similarly, I have given it for the other compounds as well. So whichever are solid in the at the room temperature, so they'll be having the melting points which have been mentioned here. The others, wherever in the brackets BP is written, that is a boiling point. So those are the liquid samples. So I have given the respective boiling points also. So please be thorough with the melting and boiling points of all of these important compounds. So especially the compounds which will be regularly given. So especially like aniline, glucose, urea. So whichever compounds have been given for practice, for your practice practicals. So be very thorough with those physical constants of those particular compounds. So this is again the list of the other compounds. So these are the possible compounds which can be given the for your analysis, for your organic analysis. So you can just make a note of all of these. So next, coming on to the detection of elements. One more simple tip I would like to add here for with respect to the boiling point and the melting point. Since we need to save time whenever we are going to do the experiments, so limited time will be there which will be given to you. So you need to find out what is the given compound, as well as you need to write down the steps, everything. So it will take a lot of time. So for that sake, first, you can find out what is the compound based on the various tests that are used, the preliminary test, the solubility test, as well as the detection of elements. All these are very important. Based on that, you'll be getting an idea about what is the group to which the compound is belonging to. And from there, after finding out, after performing the functional group analysis, you'll be getting an idea about what is that given compound. And then only you can go for the determination of the boiling point or the melting point. Because first itself, if you're going to spend more of your time in determination of this physical constants, then there may be time constraints. So because of which you may not get enough time to perform all the other tests that are required. Right. So next, coming on to the detection of elements. So the third step that is required in order to be performed during organic analysis. So let us try to understand how we need to prepare the sodium fusion extract or the stock solution, which is also called as the Lassane's extract. So firstly, you need to take a small, freshly cut small piece of sodium, and then you're going to transfer it to the fusion tube. Okay, so here we are not going to take a test tube. This is a very small tube, which is called as the fusion tube. So this particular small piece of sodium is transferred to the fusion tube. After it is transferred, then what you're going to do, you're going to warm it gently so that you're going to get a globule. Okay, so you're going to get a shining globule of sodium. And after that, you're going to add a pinch or a drop of the substance. So suppose you've got the solids sample, then you're going to add a pinch of that particular sample. Or if you've got a liquid particular sample, then you're going to add a drop of that particular sample to this silver globule that is formed because of heating of sodium. Now, after that, you're going to heat the fusion tube until it becomes red hot. So intense heat. So here you can see intense heating is done so that the fusion tube becomes red hot, where the fusion of sodium and the organic compound that is given to you takes place, which is very much required in order to do the analysis. So after that, what you're going to do, after it becomes red hot, you're going to plunge this tube, the red hot fusion tube, into around 10 ml of distilled water, which is taken in the mortar. Okay, so after it is added to the mortar, you're going to crush the tube using the pestle. Okay, so this is the pestle. I hope you all know this is the pestle, and this is the mortar. So you're going to crush. So what you can do is, for best results, you can take at least 3 fusion tubes. You can take small piece of sodium in all of these 3 fusion tubes, one by one, and then you're going to heat it, make it a silver globule, and then you're going to add the sample, and then heat it, make it red hot, and then plunge into the mortar. Okay, which is having already the distilled water which is taken, and take minimum amount of distilled water. Don't take it more because it may become more diluted. So after that, you're going to, so 3 fusion tubes, you're going to repeat the same experiment using 3 fusion tubes, and then you're going to crush it with the pestle. Okay, so that enough amount of Lassane's extract is prepared. So once it is done, what you're going to do after it is crushed well, you're going to transfer the contents into the beaker, and later you're going to boil it so that whatever the extra solvent is there, it will just be removed off, right? Now the concentrated solution, you're going to filter it. So after filtering, the filtrate, whatever you're going to get, that is used as the stock solution. Okay, so now using the stock solution, you're going to test for the various elements, especially you're going to test for nitrogen, sulfur, as well as halogen. So before that, let us see what happens during this sodium fusion extract preparation. So first of all, as I already told, this particular step is carried out in order to convert the covalently bonded atoms to ionic. Okay, so this particular step mainly converts the covalent compounds into ionic compounds. So whatever the covalent bonds are there, that will be converted into ionic bonds so that the further test becomes more easy, because the ionic compounds, they react faster, right? So you get a faster result. So for that sake, we are going to do this sodium fusion extract, or this particular stock solution is prepared, where the sodium, now in this case, so first it combines with carbon. Now suppose if there is nitrogen in the given compound, then it will form NaCN, sodium cyanide, which is ionic in nature, so that it easily gives you the result. Right. So suppose now the compound contains sulfur, then sodium will combine with sulfur that is present in the given organic compound to form sodium sulfide. Right. So again, sodium sulfide is ionic in nature, which will give you better results and faster results. Right. So next is, if there is halogen that is present in the compound, then the sodium fuses with it, because of the fusion, the sodium combines with the halogen that is present in the given organic compound to give sodium halide. So especially here, halogen can be chlorine, bromine, or iodine. But especially in this case, the chlorobenzene will be the one, the organic compound, which will be most probably given. So we are talking about chlorine in specific. Okay. So next, coming on to the test for elements. So using the stock solution, you're going to test for the various elements, especially the nitrogen, sulfur, as well as the halogens. Okay. So now let us look into how to test for nitrogen. So experiment is very simple. You're going to take the stock solution. Then you're going to add freshly prepared ferrous sulfate solution. Here mainly you need to add the freshly prepared ferrous sulfate solution, because if it is already prepared, then some of the Fe2 plus ions may have already been oxidized to Fe3 plus ions. And then what you're going to do, you're going to boil it well, and then you're going to cool the solution and then add dilute sulfuric acid. So on acidification, if you're observing a blue or green solution, then we say that nitrogen is present. Let us look into the reaction for the same. So we have FeSO4. This on reaction with sodium cyanide. Sodium cyanide, as you all know, it is formed because of the fusion of sodium with the carbon and nitrogen of the organic compound. So this forms the complex, that is sodium ferrocyanide, Na4FeCN6. This is sodium ferrocyanide. Along with that, there is sodium sulfate that is produced. So let us balance the equation. So here 6. Right. So now this sodium ferrocyanide, again, Na4FeCN6 with FeCl3, it is going to form Fe4FeCN6, which is responsible for the formation of the Prussian blue color or the Prussian blue precipitate. Okay, so NaCl. So let us balance the equation. So 12 here, 4 here, as well as 3 here. Right. Suppose we are talking about the test for sulfur. So we are going to take the stock solution. We are going to add 1 ml of sodium nitroprusside solution. Now, if the purple color is produced on shaking the solution, then we are going to observe, we are going to confirm that sulfur is present in the given compound. So let us see how the reaction proceeds. So we know that on fusion, on preparing the stock solution by the sodium fusion extract method, so we are going to get sodium sulfide, the ionic sodium sulfide. Now, this on reaction with Na2FeCN5NO, that is sodium nitroprusside, you're going to get Na4FeCN5NOS. Okay, the complex in which sulfur is also incorporated into the coordination complex. So now this particular complex has purple color. So because of which we can say that sulfur is present if the purple color appears during this particular reaction. Right. So next is test for halogens. So the experiment is very simple. You're going to take the stock solution, that is the sodium fusion extract. Then you're going to add 2 drops of concentrated HNO3. Now you're going to boil this particular solution and again cool it. So you can see here it is boiled, it is cooled, and then to this you're going to add AgNO3 solution, silver nitrate solution, dropwise. So when you add silver nitrate solution, you can easily see here that the white precipitate is formed, right? As you go on adding it in drops, you're going to get the white precipitate. You can see that the precipitate of the AgCl is formed. Now, what you're going to do is you're going to add NH4OH to this. Okay, so to this particular, once the precipitate is formed, you're going to add ammonium hydroxide. Now this white precipitate dissolves in the ammonium hydroxide. You have to add certain excess of ammonium hydroxide. Now, if this white precipitate is soluble in ammonium hydroxide, then it is confirmed that chlorine is present in the given organic compound. So white precipitate soluble in excess ammonium hydroxide, it says that chlorine is present. So how do we write the reaction? So sodium chloride is formed because of the fusion of sodium with the halogen that is present. So we are talking about chlorine here. So NaCl. Now when silver nitrate is added, we know that it forms the AgCl, the white precipitate that is formed along with sodium nitrate. So this is the precipitate that is formed. Now to this AgCl, when ammonium hydroxide is added, NH4OH, you're going to get Ag, NH3 twice Cl. Okay, so this particular complex is soluble. So because of which you can see that here you get a clear solution. So next, very important step, that is the solubility test. So here you're going to check based on this particular table. Very important, you need to look into each of the steps very clearly. First, what you're going to do, you're going to take a small amount of the sample. You're going to dissolve this sample in the particular solvent for which you're going to check the solubility. And always remember, you're going to take the ratio in 1:3. So 1 portion of the sample and 3 portions of the solvent. So this is how the solubility has to be checked. And always take only small amount of the sample for each of the test. So first, when you check for the solubility in water, suppose if it is soluble in water, then we are going to check whether it is soluble in ether or whether it is insoluble in ether. So this is the first step. First, check it in water. If it is soluble, then you're going to check whether it is soluble in ether or insoluble in ether. So suppose if it is soluble in ether, then the given compound belongs to group 1. It may be lower ketones, that is, it may be acetone or it may be resorcinol. Suppose if it is soluble in water but insoluble in ether, then the given compound may be urea or it may be glucose. So just with this, now suppose you've got urea, it is very simple. First of all, in ignition test, you get an idea. Again, when you do the copper wire test, again you get an idea that with the green edged flame, it may be urea. When you do the solubility test, by now it will be almost clear. Suppose if it is soluble in water and insoluble in ether, then by now it will be almost sure that the given compound may be urea. So suppose if the compound is glucose, which is given to you, again it will be almost clear when you do the solubility test, because when you do the ignition test, you can see that the particular substance is charred, right? It will give a black residue. By now, when you do the solubility test, if you can see that it is water soluble and ether insoluble, so by now it will be almost clear that the given compound may be glucose. So if these two compounds are given to you, it is quite simple for identification of the compounds and to go about with the further analysis. Coming on to the other part, where the given compound, when you check for water solubility, it is found that it is insoluble. Then we need to check for dilute HCl. Suppose if the given compound is soluble in dilute HCl or not. Now, if it is soluble, then we can say that the given compound may be aniline. Suppose if it is a brown liquid that is given to you, and when you do the solubility test, you can see that it is soluble in dilute HCl, then it will be almost sure that the given compound is aniline. And aniline also can be identified with the fishy odor. So it is quite simple. So suppose if aniline is given, first thing, if a brown liquid is given, first you check the smell. So suppose if the odor is fishy odor, you get an idea it may be aniline. Then you check for the presence of nitrogen. So if nitrogen is present by making use of the sodium fusion extract, so almost you'll be sure that it may be aniline. Then check for the solubility test. If it is water insoluble and soluble in dilute HCl, you'll be almost sure that the given compound may be aniline. Right. So this is another trick. Suppose if the brown liquid that is aniline is given to you. So with the solubility test itself, most of the compounds you can be almost sure which is the given unknown organic compound that is given to you for analysis. Next, coming on to If it is insoluble, then obviously you're going for dilute NaOH. So now what happens is, so suppose if it is soluble in dilute NaOH, then it may be phenol, it may be carboxylic acid, that is, it may be salicylic acid or benzoic acid. So again, so salicylic acid and benzoic acid. So suppose if these are acids, so you're going to directly do the functional group analysis where you're going to check it with sodium bicarbonate. So suppose if brisk effervescence is obtained with this particular compound, if it is soluble in dilute NaOH, then you can easily say that it may be a carboxylic acid. So I'll come to that when I'm explaining about group 4 analysis. But for now, once you get this particular test in the solubility test, if it is soluble in dilute NaOH, you have only two options. It may be a phenol or a carboxylic acid. Next is concentrated sulfuric acid. So now you need to keep in mind one more thing. Before doing the solubility test, you'll be also checking for the elements, right? Suppose if it is containing nitrogen or sulfur or halogen, right? Now, suppose if the compound contains nitrogen, so for the ones which contains nitrogen, don't go for the test with concentrated sulfuric acid, right? Because once you're checking it till here, and once you know that nitrogen is present, and again, if nitrogen is present, you need not even check for dilute NaOH, because in dilute NaOH, mainly phenols as well as carboxylic acids are the ones which are present. So obviously they don't contain nitrogen. So you need not check for dilute NaOH also. So suppose if when you do the test for elements, suppose you've got nitrogen is present, then don't check for dilute NaOH also. So once you're done with this, you can directly decide that the compound may be present here. That is, the compound belongs to group 7. Okay. So now here, as I've already told, don't check for concentrated sulfuric acid solubility if the compound contains nitrogen. So what you're going to do, so suppose if let us say compound does not have nitrogen in it, now you're going to check the solubility in concentrated sulfuric acid. If it is soluble, then it may be aldehydes, right? It may be benzaldehyde that is given, or ketone, that is acetophenol, or benzyl alcohol, or the esters. Suppose if the compound is insoluble, then it belongs to group 6. It may be hydrocarbons like toluene, naphthalene, diphenyl, or the halogen derivatives, that is chlorobenzene or the benzyl chloride, all of these. Okay. Now next, suppose we are talking about group 7. So as I've already told, once you complete the test till here, that is the dilute HCl, suppose if the compound contains nitrogen, then directly go and you're going to fill it in the group 7. You're going to decide that the compound belongs to group 7 solubility group. So now the compound may be benzamide, or it may be nitrobenzene, okay, or meta-dinitrobenzene, or anylides. So this is how you are going to decide about the various compounds based on the solubility test. The solubility test gives you a very good idea about what may be the given compound and also to which functional group it belongs to, so that your further analysis becomes more simple, more easy, as well as less time consuming. Right. So now let us look into the next step. So before that, you need to remember that you need to give a report with respect to the solubility test. So you need to report in this way. The given compound is soluble in. So which solvent it is soluble. So suppose if it is soluble in ether, then you're going to write the given compound is soluble in water and ether. Okay. So that is how you need to mention here when you're giving the report of this particular solubility test. Next, you're going to also write the given compound belongs to group. So as I've already told here, we have different groups like group 1, 2, 3, 4, 5, 6, 7. So you need to write here which solubility group that particular compound belongs to. Next, you're going to write the compound may be. So you're going to write, now suppose, let us say you've got group 4. So you're going to write the compound may be phenol or carboxylic acid. Suppose you've got group 6, let us say, then you're going to write the compound may be hydrocarbon or the halogen derivatives. If you've got group 2, then you're going to write the compound may be urea or glucose. Okay, so this is how the report has to be given with respect to the solubility test. Now coming on to the very important part of the organic analysis, that is detection of the functional group. So let us look into each of these groups one by one. So as we have already seen, we have seen that there will be group 1, group 2. So we know that different types of different compounds are included in various groups based on their solubility. Right. So now when I'm talking about group 1, so In group 1, as I've already told, we can have the ketones or the polyhydric phenols, that is, it may be resorcinol that is present. So ketones, especially only the lower ketones may be present in group 1. So let us look into group 1, that is phenol. So especially we are going to check if resorcinol is present, especially the polyhydric phenols. Okay. So first step is you're going for sodium bicarbonate test. So very simple, you're going to take the substance, you're going to add sodium bicarbonate solution. So if there is no effervescence that is observed, then acid is absent. So phenols may be present. So this is a very simple reaction to find out if the given compound may be phenol. So observation. So if effervescence is obtained, then it may be acid. And if there is no effervescence, then it is phenol. So next, this is neutral ferric chloride test, which is very important in order to check if phenol is present or not. Right. So mainly phenols, they form colored complexes with neutral ferric chloride. So the test is very simple. You're going to take the substance, you're going to add water, and to that you're going to add 1 drop of neutral ferric chloride solution. Now, after that, you're going to shake the mixture well. So suppose if violet color is formed, you can see here the violet color formation. So if the violet color is formed, then we can say that phenols are present. So let us look into the reaction for the same. So we have resorcinol. So it has here 2 OH groups. Along with that, you're going to treat it with FeCl3. So we have here O minus, OH. So thrice Fe. Along with that, there is HCl that is obtained. So here I have to balance the equation. So 3 times. Okay. So this is with respect to how the resorcinol reacts with FeCl3 to give the complex. This is violet or purple in color. Okay. So now let us look into the Lieberman's nitroso reaction. You're going to take a dry test tube in which you're going to take the resorcinol sample. To this, you're going to add equal amount of sodium nitrite crystals. Now, 2 drops of concentrated sulfuric acid is added to this. After that, you're going to warm the mixture. Once it is warmed, you're going to cool it and you're going to add water. So when water is added, you can see it is red in color. Now, to this, when you're adding NaOH solution, you can see that it turns into green or blue. So when this happens, it is clear that the presence of phenol is confirmed. So let us look into the reaction for the same. So here we know that first of all, sodium nitrite is taken. So NaNO2. This in the presence of sulfuric acid. So H2SO4. You're going to get the nitrous acid, HNO2. This is nitrous acid. Along with that, you have NaHSO4. So now, next is nitrization that takes place. Nitrization of resorcinol. So here, during nitrization, you can see that C6H4OH twice. So this is resorcinol, right? This in the presence of HNO2. It gives para-nitroso resorcinol along with water. So para-nitroso resorcinol can also exist as resorcinol quinone monoxide. Okay, so this happens in the presence of concentrated H2SO4. Now this resorcinol quinone monoxide on addition of NaOH, what is going to happen is it reacts with one more resorcinol molecule in order to form a dye which is called as the indophenol dye. Okay, so let us write the reaction. So resorcinol quinone monoxide in the presence of NaOH, it reacts with one more resorcinol molecule. This happens in the presence of NaOH to give indophenol dye. So because of the formation of this dye, you can see that there is deep blue color that is formed in the reaction. Okay. So next, coming on to the phthalate fusion test. Let us look into the group 2 analysis. That is, in the group 2, we may have urea or glucose that is given as the compounds. So how to test for urea? So first reaction or the first test that we are going to perform is you're going to take the substance, that is the urea sample. then you're going to add 10% of NaOH solution to the substance. So now so first of all, you're going to take the substance in the test tube. To this, you're going to add 10% NaOH solution and you're going to boil it. Once you boil it, you can see some vapors are released. Now these vapors are exposed to the moist red litmus paper. Okay, so red litmus paper you need to take. The moist red litmus paper you're going to take. So when these vapors are exposed to the moist red litmus paper, you can see that the red litmus paper turns into blue. So when this happens, we can say that urea is present in the given. So the given compound is nothing but urea. So let us look into the equation for the same. So we have, first of all, we know that it is urea now. So we need to write the equation regarding this particular compound when it is reacting with NaOH. So we have NH2, CO, NH2 with NaOH. So we are going to add NaOH, right, in the reaction. So we get NH3 along with that Na2CO3. So the NH3 vapors are produced. So this NH3 vapors, when it is exposed to the moist red litmus paper, it is going to turn the color of the red litmus paper to blue because of its basic nature. So this is what happens during the reaction. So this is with respect to the red litmus test, which we are going to perform when urea is given to us. So next is the biuret test. So mainly on heating, the urea forms biuret, which gives a violet colored complex with copper ions in alkaline medium. So how do we perform this test? So you're going to take the substance in the dry test tube again. So urea sample you're going to take and you're going to heat it until it fuses. Now, after it is cooled, you're going to add 10% NaOH solution and also you're going to add a drop of copper sulfate to it. After adding the copper sulfate, you're going to shake it. So when the contents of the test tube is shaken, so we can see that violet color is formed. So from this, what we can understand that? We can understand that urea is present and also it is conformed. So how do we write the equation for the same? So let us look into it. So here, first of all, we have urea, NH2, CO, NH2. This on heating, you're going to get the biuret, that is NH2, CO, NH, CO, NH2, along with that NH3, right? So let us balance the equation. So 2 moles. So this is the biuret. Now this biuret, when you're going to treat it with the, so in the presence of copper, that is Cu2 plus ions as well as the NaOH, then you're going to get the complex. So what happens is you're going to get here the complex copper, NH, CO, here again NH, CO, NH, bond. So here also NH, C double bond O, NH, C double bond O, NH, and bond here. So the total charge of +2. So this particular complex has a violet color. Okay, so this is with respect to the violet copper to biuret complex. Along with that, you also get the byproducts, that is sodium sulfate as well as water. Okay, so this happens when in the presence of NaOH as well as copper Cu2 plus ions, you're going to get this complex, that is which is also called as copper to biuret complex, that is Cu2 biuret complex, right? So this gives the violet color. So because of this visible result, we can easily say that urea is present. So whatever the compound that has been given is urea. So next, coming on to the test for sugars. So tolerance test. So first what you're going to do is you're going to take the substance, that is glucose sample, and then to this you're going to add the tolerance reagent. Now, once you add the tolerance reagent, you're going to take it in a water bath. You're not going to heat it directly. You're going to heat it in a water bath. So mainly you're going to warm this mixture, that is the mixture of these substance as well as the tolerance reagent in a water bath. And then you're going to see the formation of any precipitate. So suppose if a silver mirror or a black precipitate is formed, then we can say that glucose is present, right? So let us look into the equation for the same. So we have here Glucose I can write generally as CHO. Here CHOH 4 times. Here CH2OH. So this is glucose. So on reaction with the Tollens reagent, so we have here the oxidation of the CHO group. So COOH. Here we have CHOH 4 times. Again CH2OH, which is nothing but here gluconic acid, which is produced because of the oxidation. Now glucose undergoes oxidation. Now Ag2O is undergoing reduction to Ag. So 2 here, yes, it is balanced. So this, whatever the precipitation is seen, is forming the black precipitate, which is easily visible during this reaction. So from this, we can easily say that here the glucose is undergoing oxidation to gluconic acid and the Tollens reagent is reduced to silver. So because of which you either see the silver mirror or the black precipitate that is formed. So once you observe this black precipitate or the silver mirror, then it is confirmed that the glucose is the given compound. So let us look into the other test that you need to perform in order to confirm the presence of glucose. So we go for Felling's test. So first of all, again, you're going to take the substance in a test tube. To this, you're going to add the Felling solution A and Felling solution B. So both you're going to take equal volumes of both the solutions, Felling solution A and Felling solution B. And you're going to warm this mixture in a water bath. So once you're going to warm it, you're going to observe the color changes that is formed. So you can see that the red precipitate, the brick red precipitate of cuprous oxide takes place, because of which we can infer that glucose is the given compound. Right. So let us look into the equation for the same. So we have again CHO. I can write glucose is in this way. So CHOH 4 times CH2OH. So this is glucose. Right. To this you're going to add the copper oxide. Right. So this is nothing but the Felling's reagent. So then we have here COOH, CHOH 4 times, CH2OH. Here you're going to get Cu2O, the red precipitate. Right? Now we have here, I have to balance the equation here 2 times. Yes, it is balanced. Okay. So again, you're going to get the gluconic acid here. Right. So this is with respect to the Felling's test. Next, talking about the Mollis test. So let us look into how to perform the test. So you're going to take the substance dissolved in water. Okay. So first you're going to dissolve the given substance in water. So we know that the substances belonging to the group 1 and group 2, mainly they are water soluble. Then we are going to decide whether they are belonging to the group 1 or group 2 based on whether they are soluble in ether or not, right? So we are going to take the substance dissolved in water, and then to this you're going to add 2 drops of alcoholic alpha naphthol. Okay, so this is the next step. After you're going to add it, you're going to shake the mixture very well. Now to this, you're going to add the concentrated sulfuric acid slowly, carefully along the sides of the test tube. So once you're going to add along the sides of the test tube, you can see that the violet or the purple ring is formed at the junction of the 2 layers. So if this violet or purple color is formed at the junction of the 2 layers, then we can say that glucose is confirmed. Right. So let us look into how to write the equation for the same. That is what happens when the sulfuric acid is formed, and also how you can see that finally the violet color that is formed as at the junction. So let us look into the equation. So first, let me write the structure of glucose clearly now. OH here, H. So H and OH. Here we have COH, H. Here we have again OH and H. Then we have CH2OH, right? To this, in the presence of sulfuric acid now, there is dehydration that is taking place. 3 water molecules are lost. So we are going to get here carbon. Here again double bond. Here we have CH2OH. And here I'm going to have the CHO, which are present in the terminal carbon atoms. And here we have the H, the hydrogen atoms. Okay, so this is the first step by the dehydration of the glucose. So once you get this compound, so you're going to treat it with the alpha naphthol because you're going to add alpha naphthol in the test, right? So let us write the structure of alpha naphthol. So this is alpha naphthol. There is a OH group. So here there will be a OH group. So now this on reaction with alpha naphthol, again there is a loss of water molecule in the presence of concentrated sulfuric acid. So you're going to get here whatever is present here. So here the furan ring is present. Along with that, the CH2OH remains as such. So here the alpha naphthol comes and binds. So here a double-membered, a six-membered double ring is present. So OH is present here. Now again, since I've taken here 2 moles of alpha naphthol, so one more alpha naphthol group will be attached here. So double bond here. So we have again a benzene ring with the OH group, right? So now again, we know that there is sulfuric acid that is present. So because of which you can see that here the furan ring is as such, here CH2OH. So now we have here the conjugation continues. Okay, so you can see here the benzene ring. Then we have double bond. So already a conjugated system. Along with that, you can see here also. Now we can see here the double bond that is present. Now here OH, the plus charge. Okay, so this is how the conjugation continues in the presence of oxygen. That is again because of the presence of sulfuric acid that is added in the reaction mixture. So next, coming on to the group third. Okay, so we have already discussed how to perform the various tests for group 1 and group 2 based on the solubility groups. So now let us look into how to detect the presence of the various compounds under group 3. So mainly under group 3, we are looking into aniline, that is amines. So let us look into how to perform the various tests. So first of all, we are talking about acylation. So we're going to take, again, in this case, you have to be very careful. You're going to take a dry test tube. So you're going to take a dry test tube. To this, you're going to add the substance. You're going to take the substance in the dry test tube. To this, you're going to add the acetyl chloride or the benzoyl chloride solution. Okay, so this is how the acetylation or acylation is done. So especially this acetyl chloride or benzoyl chloride, when you're taking, they are highly reactive. So we have to be very careful. So for that sake, we are going to take the dry test tube. Okay, so now what happens? The vigorous reaction takes place and there is the liberation of heat. So temperature rises rapidly. So when this happens, it is very clear that primary amine is present. So let us look into what is the equation for this particular reaction. So first of all, here we are talking about aniline. So C6H5NH2. Now we are going to add acetyl chloride, which is CH3COCl. So you get C6H5NHCOCH3, which is nothing but acetanilide. So acetanilide is obtained. Along with that, you also get acetic acid, CH3COOH. So now here there is liberation of heat and this particular reaction is highly vigorous. So because of which you have to be very careful while performing this acylation reaction. So next test is carbylamine test. So this also we should perform very carefully. And one more thing is that usually in the laboratory, they don't go for performing this particular test because it gives out a very obnoxious smell, as well as we can say that it is a strong smell. Okay, so this particular test is avoided, which is to be performed in the laboratory. So you can directly write what is the test along with the principle of the same. So here carbylamine test, you're going to take the substance, okay, in the test tube, and you're going to add alcoholic NaOH solution to this substance. Then to this, you're going to add chloroform solution dropwise. So once you're going to add this, and then you're going to warm this particular mixture, now you can see that obnoxious smell is detected. Okay, so this obnoxious smell is mainly because of the isocyanides which are produced in this particular reaction. So we can say that primary amine is present. So whatever the compound that is given is a primary amine. So we know that obviously the aniline is a primary amine. So if you perform this experiment in the presence of aniline, so when you add this alcoholic NaOH as well as chloroform and warm with the aniline, then you can see that isocyanide is formed, which will result in the obnoxious smell. So usually it is seen that this particular test is avoided. Okay, so let us look into the equation for the same. So we take aniline. So Ar is nothing but C6H5. So to this, you're going to add the chloroform, and then you can add NaOH or KOH. It is completely fine. So you're going to get your ArNC, that is isocyanide. Along with that, you're going to get NaCl and H2O, right? So 3 here and 3 here. So yes, I think it is balanced. So here, this is nothing but the isocyanide that is formed, which will result in the obnoxious smell, right? So next, coming on to the important test, that is diazotization reaction. So for this, what you're going to do is you're going to take the aniline, okay? That is here, obviously, they'll be giving you aniline, which will be detected under the third group in the solubility test. So we're going to take the aniline, and then to this, you're going to add the dilute HCl. Now, once you take this, you're going to shake to dissolve it, because we know that aniline belongs to the third group in the solubility chart. We have seen that. So in the third group, we know that we decide that aniline belongs to this particular group because it is soluble in dilute HCl. So obviously it is going to dissolve. So you're going to shake this solution so that it dissolves in dilute HCl, and then you're going to cool it in ice. So this particular diazotization reaction has to be carried out at very low temperatures, especially at 0 to 5 degrees Celsius. Right. So once it is done, you're going to add ice-cooled solution of NaNO2. Okay. So all of these steps have to be carried out at a very low temperature, as I've already told. Now, this clear solution, whatever you're going to get, you're going to add beta-naphthol. Okay, beta-naphthol in NaOH. You're going to mix the two solutions. Now, you're going to get the bright orange red dye that is obtained. So then we can say that aromatic primary amine is confirmed. So obviously, we know that aniline is a primary amine, and specifically, it is also an aromatic amine, right? So aromatic primary amine, which is nothing but aniline, is confirmed here. So let us look into the reaction for the same. So first of all, you're going to have aniline, so ArNH2, in the presence of nitrous acid. That is, you're going to take NaNO2, HCl, and at a 0 degree Celsius. Now we are going to get the diazonium chloride, benzene diazonium chloride. Along with that, there is water that is produced. Now this benzene diazonium chloride, in the presence of the beta-naphthol, so the coupling reaction takes place. So this is beta-naphthol. So here, in the presence of NaOH, the coupling reaction takes place to give the bright orange red dye, right? So we have here, so here N double bond N, Ar, and here there is OH anyways. So here bright orange red dye is obtained. Along with that, there is HCl that is obtained. Right. So this is a very important reaction, that is even with respect to the Viva. So they can ask you to write the equation that is involved in the diazotization reaction. So you need to write this and explain how the reaction takes place. So this is about group 3. So let us now look into group 4. So we have already discussed for group 1, group 2, and group 3, the functional group analysis. Now let us look into group 4, which includes the phenols and acids. So let us look into the first step, the first test, that is sodium bicarbonate test. So you're going to take the substance. To that, you're going to add the sodium bicarbonate, that is NaHCO3. Now, you're going to add the sodium bicarbonate solution drop by drop. So when you add it, so if there is an effervescence, if there is a weak effervescence, then we can say that acid is present. If there is no effervescence that is obtained, then we can say that the given sample may be phenol. Right. So let us look into the further test that we need to carry out in order to confirm whether the given compound is a phenol or an acid. So first, let us look into how to test for acids. So before that, I hope you know already how to write this equation. So let us write it and then let us go to the next test. So we have in this case, the RCOOH, because we know that sodium bicarbonate is going to react with the carboxylic acid. So RCOOH plus sodium bicarbonate, it is going to give you RCOONA plus carbon dioxide along with that water, right? So this is with respect to this reaction. And since there is CO2 that is produced in the reaction, you can see the effervescence that is obtained, right? So let us look into the second reaction now, how to find out if the compound is an acid. So let us say there is effervescence that is obtained. So now we know that the given compound is a carboxylic acid. So let us look into the various tests that you need to perform to check that, to confirm that the given compound is an acid. So now we go for esterification reaction. So for the confirmation of the carboxylic acid, we go for esterification. So you're going to take the substance in the dry test tube again, because here again you're going to add concentrated sulfuric acid. We need to keep one thing very clear in our minds. That is, whenever concentrated sulfuric acid is added in the test, it should be very clear that the dry test tube has to be used. The glassware should be dry. Okay, so you're going to take the dry test tube. You're going to take the substance in the dry test tube. To this, you're going to add ethyl alcohol, and then you're going to add concentrated sulfuric acid drop by drop. After this, you're going to heat the mixture, and then you're going to pour it into sodium carbonate solution. Okay, so now once you pour it to the sodium carbonate solution, if a fruity odor is detected, then it is confirmed that the acid is given to you. So let us now look into how to write the equation for the same. Okay, so yes, so we have RCOOH, that is the carboxylic acid that is given. Now to this, you're going to add the ethanol in the reaction. So in the presence of H plus mineral acid, that is here we have used concentrated sulfuric acid, which acts as a catalyst. So we have RCOO, C2H5, along with that water is produced. Now, why is sodium carbonate added? After the esterification is done, why do you think you need to add sodium carbonate? So we have seen that the mixture is poured into Na2CO3 solution, right? Sodium carbonate solution. Here, the reason, so they can ask you this particular question in Viva. So mainly the sodium carbonate is used to remove the excess of sulfuric acid that is added, as well as if there is any unreacted carboxylic acid. So here, what happens is the sulfuric acid, if there is anything in excess, it reacts with sodium carbonate to give sodium sulfate, along with that carbon dioxide and water. So if there was any unreacted carboxylic acid, it also reacts with the sodium carbonate to give the sodium salt of the carboxylic acid along with that carbon dioxide and water, right? So this is with respect to, so this question can be asked as a very important Viva question where they can ask why you need to add sodium carbonate after the esterification is done. So this is the reason. Okay. So now we have seen how to confirm the presence of acid, right? So now we know that the acids, mainly the ones which are given, are either the salicylic acid or the benzoic acid. So now we need to differentiate between the two acids. You need to identify which is the carboxylic acid that is given to you. So we go for the distinguishing test between salicylic acid as well as the benzoic acid. Very simple. You're going to take the substance. Okay. You're going to take the solution of the substance in water, and then you're going to add a drop of ferric chloride. Okay. So when you add ferric chloride, if a violet color is observed, then we can say that salicylic acid is present. Suppose now the same test, if you're going to take the substance and add it to water, to this you're going to add a drop of neutral ferric chloride. Now, if there is no violet color that is obtained, then we can say that the benzoic acid is given to you. Okay, now the question is why salicylic acid can give the violet color like that of phenols when the ferric chloride is added. It is very clear that in the salicylic acid, there is one OH group which is directly attached to the benzene ring like that of the phenol. So because of which it gives the positive test with the neutral ferric chloride. Okay, so let us look into the equation. So salicylic acid, we have the OH group which is directly attached to the benzene ring. So obviously there is one COOH group also, because of which it is a carboxylic acid. Now this on reacting with FeCl3, neutral ferric chloride, we get Fe. So here C6H4 COOH thrice. So this complex is obtained along with that 3HCl. Okay, so this is nothing but the violet ferric salicylate complex. Okay, so let us balance the equation. So here 3 times. Right. So I hope it is clear. So only if you are using the salicylic acid, if that is the compound that is given to you under group 4, so then we know that if the violet color is obtained, then it is salicylic acid. If the violet color is not obtained, then it may be benzoic acid. Okay, so this is with respect to the acids. We have seen the different confirmatory tests. One is the esterification. Then we need to go for first of all, sodium bicarbonate test will tell you that the given compound is an acid based on the effervescence that is obtained. Then you go for esterification. Then finally, you're going to distinguish between the two acids, whether it is benzoic acid or salicylic acid, based on the neutral ferric chloride test. Right. So next coming on to the test for phenol. So as we already know, under group 4, there can be acids, that is carboxylic acids or phenols that may be given. So first test, it is common, that is sodium bicarbonate, which you're going to add. So when sodium bicarbonate solution is added, if there is no effervescence, then you directly decide that the given compound is a phenol because we're testing for group 4, right? So now, next test coming on to neutral ferric chloride test. So now how you're going to perform this? So very simple. So substance along with water. Now to this, you're going to add the neutral ferric chloride solution. Suppose you get a violet color, then we know that the phenol is present. Just we have seen for salicylic acid, the similar test. So same thing is done here. So if a violet color is produced, so we can say that the phenol is present. So let us look into the equation for the same. C6H5OH plus FeCl3. So we have here FeOC6H5 6 times 3 minus, along with that H plus and chloride ions. So here we have 6, right? So this is with respect to the complex that is formed, which is the iron phenol complex, which is violet in color. Yes. So this is already the reaction which we have already conducted even for the resorcinol. So similar reaction, but here we are talking specifically about phenols. Okay. So next reaction, the next test what we need to conduct for the phenols is that the phthalate fusion test. So here what you're going to do is you're going to take the substance again in a dry test tube. To this, you're going to add 1 crystal of phthalic anhydride. Now, again, you're going to add 1 drop of concentrated sulfuric acid. You're going to heat until it melts, cool it, and then you're going to add NaOH solution. But now, here the observation is that you're going to get the pink color. If the pink color is obtained, then we can say that phenol is confirmed. So let us look into the reaction for the same. Here mainly it is the phenolphthalein that is obtained, because of which you can see that there is a pink color that is obtained, because here you're going to add the NaOH solution. So in the basic medium, it is pink in color, right? So first of all, you're going to take the phthalic anhydride, right? So this is phthalic anhydride. To this, you're going to add the phenol. So substance plus phthalic anhydride, right? So we have phenol. So 2 moles. So it reacts in 1:2 proportion. So in the presence of concentrated sulfuric acid. So here, the benzene ring of the phthalic anhydride. So here we have, here the double bond remains, and here the addition takes place of the coordination with the different rings takes place here with the phenol rings. So here it attacks, and here also here the phenol rings attaches to the phthalic anhydride. Now, here we have H2O. So this is in the acidic conditions, right? So in the acidic condition, the phenolphthalein is colorless. Now we know that we are going to add the base NaOH, right? So in the presence of base, we know that it is color. Phenolphthalein is color. It is pink in color. So now the conjugation changes. So you can see here, this becomes C double bond O minus. Now here we have this phenol ring that is present. It remains as such, OH. Now here, this phenol ring, here you can see that there is conjugation. And because of this, this conjugation that is taking place, as well as here you can see this particular cyclic structure breaks. So here the phenolphthalein is pink because it is in the basic medium. Right. So this is how you can see that a pink color is observed when you add sodium hydroxide. So mainly the basic idea here is the phenolphthalein is produced and this gives pink color when you're going to add the base. So let us look into the next test. So we are looking into the different tests that have to be conducted if phenol is given. So first we look into neutral ferric chloride test, and then we also check onto the ethylene fusion test. So now let us look into Lieberman's nitroso reaction. So let us look into it. So first of all, you're going to take the one crystal of the substance. So here you're going to take the phenol. So you can take the substance, and then you're going to take equal amount of sodium nitrite crystals. So phenol will be in the liquid state. You're going to add sodium nitrite. And then to this, you're going to again add 1 drop of concentrated sulfuric acid. Now warm it. After warming, you're going to cool it. And then you're going to add water. Okay. So first, when you add water, it was red. Now, when you add NaOH solution, you're going to see that the red color is going to change into blue or green. Like how we have observed for resorcinol, the same thing happens here. So as you remember, we have seen that in resorcinol, the indophenol dye was formed. So here also the indophenol dye is formed. Okay. So let us look into the reaction for the same. So we are going to take the sodium nitrite, right, in the presence of sulfuric acid. So you're going to get the nitrous acid, HNO2, along with that NaHSO4, right? So here we have nitrous acid that is produced. Now we have the phenol, so C6H5OH in the presence of this nitrous acid. And obviously there is concentrated sulfuric acid that is added, right? So you're going to get C6H4NO. So nitrosophenol, para-nitrosophenol is obtained. Along with that, water is produced. Now this para-nitrosophenol, C6H4NO, it reacts with one more molecule of phenol in the presence of sodium hydroxide. Like how we have seen in resorcinol, the same reaction occurs here, because resorcinol is also a type of phenol, right? It is a dihydric phenol. Here, phenol is just having one OH group attached to the benzene ring. So here you're going to get the indophenol dye, which is blue or green. So because of this formation of the indophenol dye, which is blue or green in color, you can see that when you add NaOH, you can see that the color changes to blue or green. I hope it is clear. So this is with respect to the group of 4 analysis. So how you are going to do the analysis? Mainly you're going to check for the presence of acids, that is carboxylic acids or phenols, and each of them have specific test. Now let us go to group 5 analysis, which consists mainly of aldehydes, ketones, alcohols, or the esters. So we are going to see each of the tests one by one along with the respective reactions. So let us look into how to test for aldehydes and ketones. So first of all, we are going to do the 2,4-DNP test. So you're going to take the substance, that is aldehyde of the ketone sample, in the test tube. Then you're going to add 4 to 5 drops of 2,4-DNP. Now, once you add 2,4-DNP to this, so you can see that once you shake the contents of the test tube, you can see that the yellow or the reddish precipitate is formed, which suggests that the aldehydes or ketones may be present. So the given compound may be an aldehyde or a ketone. So here we know that 2,4-DNP, it reacts with the aldehydes or the ketones to give the addition products. So let us see how it is formed. So C double bond O. So this is the general representation of the aldehyde or the ketone. So we are going to add the 2,4-dinitrophenyl hydrazine, right? So 2,4, right? So this on addition. So what happens is the H2O will be removed off, right? The hydrogen, the H2 of the 2,4-DNP, as well as the oxygen of the carbonyl oxygen, that is the oxygen of the carbonyl group. So they are removed as water molecules. So there is elimination of water molecule. So you can see that here, double bond, here N, NH, here the benzene ring, here we have NO2, and here we have NO2, right? So in this case, So obviously, I'm not going to write again H2O because I've already shown that the elimination of water molecule has taken place. So this is the compound that is obtained, which is nothing but 2,4-dinitrophenol hydrazone. So here it is 2,4-dinitrophenyl hydrazone. Right? So because of the formation of this 2,4-dinitrophenol hydrazone, it is either yellow or reddish precipitate. It is yellow or reddish in color. So because of which, because of the precipitation of this particular compound, we can say that the carbonyl group will be present in the given compound. So it may be an aldehyde or a ketone. So let us look into the next test. So next we are going to check if it is an aldehyde or a ketone. So to differentiate between the aldehyde or the ketone, we have the Skips reagent test. So we are going to take the test tube. So in the test tube, you are going to take the substance that is aldehyde or the ketone, to which you are going to add 4 to 5 drops of Skips reagent. Now, once you're going to add it, you're going to shake the contents of the test tube. So suppose if a pink color is formed, so if the pink color is restored, so you're going to add the Skips reagent. You're going to shake the contents. If the pink or the magenta color is restored, then we say that aldehyde is present. Suppose if there is no pink color that is observed, so we can say that the compound is a ketone. So this is a very good distinguishing test which helps us in understanding if the compound is an aldehyde or a ketone. Because in the first test, that is by making use of 2,4-DNP, we can say that a carbonyl group is present in a given compound, but we are not able to differentiate between the aldehyde or the ketone. But in this case, it is very clear that if the pink color is formed, then the given compound is aldehyde and the other one is a ketone. So if the question is asked in Viva, which test you're going to perform in order to differentiate between aldehyde and ketone, you're going to give the answer as the Skips test and also explain about how it is done. So let us look into the reaction for the same. So first of all, the Skips reagent. So here we have this structure of the Skips reagent. NH, SO2H. Here we have the carbon. Here SO3H. Again, there is one more benzene ring. Here NH and SO2H. Here again, one more benzene ring. Here it is NH2 group. This is the Skips reagent. Now this in the presence of aldehyde, we know that only in the presence of aldehyde, a pink color is observed. So again, it reacts in 1:2 ratio. So here, carbon. So let us start writing the structure. In the presence of aldehyde, what is going to happen? So here NH, here it will be SO2. So one of the aldehyde group, it attaches here, the aldehyde molecule. So here we have the conjugation that is happening. So here double bond, here NH2, the plus charge that is there on the nitrogen. Now again benzene ring. So here NH, here SO2. Again one more aldehyde molecule is attached here, right? So this is nothing but the Skiff adduct, which is magenta color. Okay, so because of this formation of the Skiff adduct between the Skiff reagent as well as the aldehyde, so the magenta colored adduct is formed, because of which you can see that a pink color is restored during this particular reaction, this test, and it is very clear that the aldehyde is given to you, right? If it is not giving the pink color, then we know that it is a ketone. So suppose you've got the pink color in this particular test, you need to confirm that the given compound is aldehyde. So we need to go for the next confirmatory test for aldehydes, that is the tolerance test. So very simple, you're going to take the tolerance reagent, you're going to add it to the sample. So first of all, the principle is aldehydes, they reduce the tolerance reagent to metallic silver. So you're going to take the substance, you're going to add the tolerance reagent, shake it, and again, you're going to warm it in the water bath. You're not going to heat it directly. You're going to use the water bath for warming. So suppose if there is a bright silver mirror, then we can say that aldehydes are confirmed. So let us look into the reaction for the same. So already we have written the reaction for glucose, half we can see that the CHO group was oxidized to COOH group. So similarly, we have the same reaction, RCHO. Now we are talking only about the aldehydes in specific. So in the presence of heat, you're going to warm it, right? So you're going to get RCOOH. So the aldehyde is getting oxidized. Along with that, you're going to get the silver. So this forms the black precipitate or the silver mirror that is obtained. Right. So the observation can be any of this. Either a black precipitate is obtained or the formation of a silver mirror on warming it on the water bath. So if this happens, we can say that the aldehyde is confirmed. So this is a confirmatory test that is used for the aldehydes. So similarly, in the Skips reagent test, when you're doing it, suppose if the pink color is not obtained, then we know that it may be a ketone that is given to you. So you need to perform the confirmatory test in order to prove that the ketone has been given. So what you're going to do, you're going to perform the confirmatory test for ketone, that is sodium nitroprusside test. So let us look into how this test is done. So first of all, in the test tube, you're going to take the substance, that is the ketone sample. To this, you're going to add the sodium nitroprusside solution. Okay. Now, once you add the solution, you're going to make the solution basic alkaline by adding sodium hydroxide solution using the dropper. You're going to shake the solution. So when you shake the contents of the test tube, you can see that a red color is obtained, which confirms the presence of ketone. So let us look into the reaction. What happens here? Why the red color is obtained? So first of all, you're going to take the ketone. So let me take the general formula. So this in the presence of sodium hydroxide. So we're going to add sodium hydroxide in the reaction, right? So it forms RCO, here CH2 minus Na plus. So one of the hydrogen from here will be abstracted by the base. So along with that, there is water that is obtained. So RCO CH2 minus. This on reaction with the sodium nitroprusside, because we are going to add sodium nitroprusside in this reaction. So now CN5NO. So this nitroprusside, sodium nitroprusside, the formula we have seen it even in the test for sulfur, right? So the same sodium nitroprusside is used here also. Now we are going to get FeCN5NO. Now the ketone also comes in coordination. So here 3 minus. So this is nothing but the red coloration is obtained because of the formation of this particular complex. So we can see that suppose if the red color is formed during this reaction, that is in the sodium nitroprusside test, we can confirm that ketone is the compound that is given to you. So by now, in the group 5 analysis, we can easily identify if the carbonyl compounds are given, and easily we can differentiate between these aldehydes and ketones, mainly by making use of the Skips test and also perform the confirmatory test for both of them. Let us now look into the next class of compounds that are included in group 5. So already we know that in group 5, it can be aldehydes, ketones, alcohols, or esters. So now let us look into, suppose if alcohols are given, then how we are going to perform the various tests. So first test that you need to perform if the given compound is alcohol, then we are going for the sodium metal test. So you're going to take the substance in a dry test tube here. So again, we have to be very careful here. The hydrogen gas is liberated in the reaction. Suppose if the alcohol is given. So that's why we have to be extra careful. And also you're going to add the sodium metal. So it easily reacts with the moisture, as you already know, because it is a highly reactive metal. So for that sake, we have to take the dry apparatus, the dry glassware. So you're going to take a dry test tube. To this, obviously, you're going to take the substance in the dry test tube. To this, you're going to add a small dry piece of sodium metal. So you can see that a brisk effervescence is obtained. So the bubbling takes place, because of which you can see that the hydrogen gas. So obviously, because hydrogen gas is liberated, you can see the bubbles that are formed. So once you can see the bubbles that are formed, we can say that the alcohol is confirmed, or we can say that the alcohol may be the compound that is given to you. So let us look into the reaction for the same. So we have our CH2OH. To this, when sodium is added, you're going to get our CH2ONA, and hydrogen gas is liberated. So let us balance the equation here, 2 and 2. Right. So Since hydrogen gas is liberated here during the reaction, we can see the bubbles that are formed, which is nothing but the brisk effervescence that is observed. Right. So now this is with respect to the first test for the detection of alcohols. So we also have to confirm the presence of alcohol. Suppose if this brisk effervescence is seen, then we need to confirm if the compound is alcohol or not. So we go for esterification reaction. So very simple, we know that esters are formed by the reaction of alcohols and carboxylic acid in the presence of mineral acid, which acts as a catalyst. So the same principle is kept in mind, and we are going to perform this test. So we are going to take the substance. So here it is the alcohol sample. Now you're going to add benzoic acid, okay, because benzoic acid is the carboxylic acid which will react with alcohol in the presence of mineral acid to give the ester. Right. Now you need to add concentrated sulfuric acid, and again keep it in mind, we are going to take a dry test tube here. We're going to add concentrated sulfuric acid. Now this sulfuric acid acts as a catalyst. Mainly it helps in catalyzing the formation of ester. Now you're going to heat it, and after heating you're going to pour the contents of the mixture into the solution of sodium carbonate. So already I explained in the test for carboxylic acid when I was explaining about esterification, why we need to pour the contents into sodium carbonate solution, because mainly if there is any unreacted acid, carboxylic acid, or unreacted sulfuric acid that is present in the reaction mixture, so that will be removed out because of the reaction with sodium carbonate. So I hope you remember that. So for that sake, we are going to pour the mixture, pour the contents of the test tube into the sodium carbonate solution. Now, suppose if a fruity odor is detected, then we know that it is the alcohol. So whatever the sample was given is alcohol, and it is confirmed. Right. So this is with respect to the confirmation test for the presence of alcohol. So let us now look into the reaction, how we are going to write the equation. So here you're going to take benzoic acid, right? You're going to add benzoic acid to the alcohol. So I'm going to take ROH. Now here you're going to get C6H5 COOR, right? Along with that, you're going to get water. And usually we say that esterification or H plus is the one which is catalyzing this reaction. And also we know that here, as water is removed during the reaction, as and when more and more water is removed in the reaction, more and more products are formed. Otherwise, this particular reaction will go for equilibrium, where again the products formed may give back the reactants. Right. So this is with respect to esterification reaction, which is a confirmation test for the presence of alcohol. So now we have seen how we are finding out if the aldehyde, ketone, or the alcohol has been given. Now, we also know that in the group 5, there is another class of compounds which may be included, that is the esters. So now let us look into how to perform various tests for the detection of esters and also for the confirmation of the same. So first test is alkaline hydrolysis test. So we take the substance, okay, and we are going to add 2 to 3 drops of NaOH and also 1 drop of phenolphthalein. So when you add NaOH and when you're going to add phenolphthalein, obviously it will be the pink color that is formed, because we know that phenolphthalein is pink in color, especially in the basic medium, right? So it becomes, the solution becomes pink. Now you're going to warm it, and slowly you're going to add the dilute HCl. Now slowly what happens, the pink color discharges. Now once you're going to add dilute HCl, okay, so you're going to add dilute HCl to it. So when you add this acid, you can see that a solid separates out. So when this observation, so first whatever the pink color is formed, it discharges. Now we are going to add dilute HCl. When you add dilute HCl, if a solid separates out, then we can say that the given compound may be an ester. So let us look into the reaction to make it more clear. So first of all, we are talking about ester here. So RCOO, R dash, this is the ester. This in the presence of NaOH. First thing you need to remember. So first we are taking the ester and NaOH, and also phenolphthalein is added. So first it will be pink in color. But what happens is, as you're taking an ester in the presence of a base, now hydrolysis of the ester takes place. Now, due to hydrolysis, you're going to get RCOONA. Along with that, you're also going to get the alcohol back. Okay, so you're going to get the sodium salt of the carboxylic acid that is used to prepare the ester, and also you're going to get back the alcohol. So now Because of this, what happens? The pink color discharges. Now there is whatever the NaOH has been added, it is used up for the hydrolysis of the ester. So the pink color discharges. So this is the reason for the first observation. Now what I've told about the second observation, if you add dilute HCl, then you can see a white solid is separating out. Now here we have this RCOONA. To this, when HCl is added, you can see that you're going to get RCOOH, which is the acid, and this is the one which is going to precipitate out. Along with that, you're going to get the NaCl. Now, one more thing, it has to be very clear. Here, we are going to take the aromatic ester, so that in this case, you're going to get the aromatic carboxylic acid that is precipitated out. So mainly if you're going to take the ester with low molecular weight, then it may not give the respective carboxylic acid may not be precipitated out. But for your organic analysis, it is usually the aromatic esters which are given. So when you're adding the dilute HCl, you can see the precipitation, especially the solid which comes out, which separates out is nothing but the carboxylic acid that is formed. Right. So this is with respect to how we are going to detect the presence of ester. So first test in order to find out if the given compound is an ester. Now to confirm the presence of the ester, we have to go for the next test, that is hydroxylamine test. So what you're going to do, you're going to take the substance, okay, in the test tube. You're going to add 3 to 4 drops of hydroxylamine hydrochloride. So here we have hydroxylamine HCl, which is nothing but hydroxylamine hydrochloride. 3 to 4 drops you're going to add. And to this, you're going to add methanolic KOH. Now, after adding all this, you're going to boil it in a water bath. After boiling in the water bath, you're going to cool it. And then you're going to add 1 drop of ferric chloride and HCl. And mainly you can see that you're going to add the HCl until it is acidic. The entire solution, whatever the contents are there, it becomes acidic in nature. You can see that the violet color is observed. So when the violet color is formed, we can say that the esters are present, and this is a confirmatory test for the presence of esters. So now let us look into the equation for the same. So now let us take RCO OR dash, the ester, in the presence of hydroxylamine hydrochloride, so NH2OH, you're going to get RCO, NHOH. Along with that, you're also going to get back the alcohol. Now, this RCO, NHOH, in the presence of ferric chloride, you're going to get RCO, NHO, thrice Fe. Along with that, you're also going to get HCl. So let us balance the equation. Here 3 and 3. Right. So this, whatever you get, the compound, what you're going to get is nothing but it is purple in color. And this is responsible for the formation of the violet color that is observed in this particular reaction. Okay. So next coming on to the group 6, that is test for hydrocarbons. So already we have seen for group 5, we have seen how to predict the presence of the aldehydes, ketones, alcohols, as well as esters. Now let us go to how to perform the various tests in order to look for the various compounds that are included under group 6. So it can be the hydrocarbons or the halo-substituted hydrocarbons. It can be the amides, nitro compounds, etc., which are included under group 6. Right. So now let us look into how to find out if the hydrocarbons are present. So first of all, you're going to take the substance. You're going to add 1 cc of concentrated sulfuric acid, because we know that these are the compounds which are present to the last group, the group 6 in the solubility test. We have seen it. So you're going to add concentrated sulfuric acid. You're going to boil until a uniform layer is formed. After that, you're going to cool it and you're going to pour the contents of the test tube into the water. So once you're pouring it, if you observe and you can see that a clear solution is observed, that is, if there is no precipitate that is formed, then we can say that hydrocarbons are present. So now, once you know that hydrocarbon is present, then we can go for further test. Okay. So why this clear solution is obtained? Let us look into the equation. So we know that hydrocarbon is present. So you're going to take sulfuric acid. So let me write it in this form, OH, SO3H. So I'm going to write this OH separately here. In the presence of heat, because you're going to heat the solution, so you're going to get ArSO3H, along with that H2O. So you're going to get the sulfonic acid derivative of the hydrocarbon. So along with that, water is also formed. So now this gives a uniform layer without the formation of any precipitate. So we can say that the hydrocarbon is present by looking at the first step. So now the next test or the next step, what we have to perform is we need to check if the halogen substituted hydrocarbon is the one which is given. So already if you can see that chlorine was present when you do the test for the halogen under the Lessines test, right? So if you have observed that chlorine was present, and also if a green edged flame was obtained when you did the ignition, when you did the copper wire test, then we can say that it may be halo substituted hydrocarbon. But still, we need to confirm it if it is a nuclear halogen that is present or the side chain halogen which is present. So let us look into how to perform this test. So the test which will help you in identifying whether the side chain halogen is present or the nuclear halogen that is present in the given compound. So you're going to take the substance, okay, which is, suppose if you have observed that halogen is present during the Lessines test, then only you're going to perform this particular test. Okay. So now what you're going to do is to this, you're going to add the alcoholic AgNO3 solution. You're going to shake it properly and warm. Okay. So suppose you see that there is a white precipitate that is obtained, then we can say that the side chain halogen is present. Suppose if there is no precipitate even on warming the solution, you can say that the nuclear halogen is present. So I repeat, this particular test is only carried out if you have got the positive test in the test for halogens when you're doing the Lessines test, okay, or the sodium fusion extract test. Now let us look into the reaction. What happens? Why white precipitate is obtained when side chain halogen is present? Why not in the case of the nuclear halogen? Okay, so let us look into the reaction. So suppose we have the nuclear reaction, the nuclear halogen that is present. So this in the presence of AgNO3. So you're going to take alcoholic AgNO3, heat, there is no precipitate that is formed. Suppose we are talking about the side chain halogen that is present, so CH2Cl. Now again, you're going to add AgNO3, alcoholic AgNO3, heat it. Here you're going to get ArCH2NO3 plus AgCl. Okay, so AgCl is nothing but it gives a white precipitate that is formed. Now, what is the reason why in this case the precipitate is not formed and why here there is precipitate that is formed? In both the case, there is chlorine, but still why there is no precipitate in the first case? So it is very clear that here in the first case, the ArCl bond that is present, it cannot be broken so easily, right? Mainly it is having a partial double bond character because here you can see that it is involved in the resonance. The electrons are delocalized and this particular bond, the CCl bond, that is carbon of the aromatic ring and the chlorine, they are involved, they are having this particular bond has a double bond, partial double bond character, mainly because of the resonance. So because of which this Cl cannot be removed off. And one more reason is that if the Cl is removed, then it results in the cation, the carbon bearing the positive charge, the carbon of the benzene ring, which is highly unstable. So it does not go for this breakage of the bond. So because of that, here we do not get any precipitate. Only in this case, so here it is very simple. This bond can break even if it breaks. So we get the cation in this way, right? CH2 plus. So it is stabilized by resonance. So this particular the breakage of this CCl bond can take place, because of which you get the AgCl precipitate. Okay, so I hope it is clear about how the side chain as well as the nuclear halogen can be detected by this simple technique. Okay, so now let us look into what about amides. So we know that amides are also present in this group 6. So how do we detect the amides as well as how do we confirm the same? So for amides, we're going to take the substance in the test tube. You're going to add NaOH solution. Now you're going to boil it and again expose this vapors, whatever are obtained, to the litmus paper. So mainly here also, like how we have done for the urea, same thing we are going to follow here also. So in this case, again, when you're going to take a moist red litmus paper, you're going to expose the vapors to this moist red litmus paper. You can see that the red color changes to blue. So we can say that amide is present. So this is a test which will help us in identifying that amide is present. Now, you can again cool this particular the solution, whatever is present, the contents of the test tube, and then you're going to again you're going to acidify this particular mixture. Okay, when you acidify the mixture by making use of dilute HCl, now you can see the solid separates out. So we can say that amide is confirmed. Okay, so this is the test for amides. So let us look into how this reaction is written for this particular test. So mainly we know that we have RCONH2, which is the amide. So usually we are going to take the aromatic amide. So first step is we are going to take NaOH and heat it. And second step is we are going to acidify the contents, right? So we have RCOOH, same like how we have discussed in urea, the same thing we are going to discuss here. So here the RCOOH, especially the aromatic, since we are taking the aromatic amides, here you're going to get the aromatic carboxylic acid, which will give out as a solid. So we have seen that suppose if aromatic carboxylic acid is there, it separates out easily. We have seen even in the hydrolysis of the ester. So same way here also we can see the white solid that is separating out, which helps us in confirming that the amide is the given compound, right? So next is with respect to the nitro hydrocarbon. So how we are going to test for the nitro compound, okay? So first of all, you're going to take the compound, you're going to add the concentrated HCl solution. Along with that, you're going to add the zinc dust. Okay, so mainly whenever we speak about zinc as well as in the presence of concentrated HCl, we know that reduction reaction takes place, correct? So now you're going to boil it, boil the contents of the test tube. You're going to cool it, and then you're going to add ice cold solution of sodium nitrite. Okay, and then you're going to perform the coupling reaction by making use of beta naphthol in NaOH. Okay, so here you're going to again get bright orange red dye. So from this, if this bright orange red dye is obtained, then we can say that the given compound is a nitro hydrocarbon. Okay. So let us look into the reaction. We are already familiar with the diazotization as well as the coupling reaction of aniline. So it is very clear here, since zinc dust and concentrated HCl is used, the reduction of the nitro compound takes place to aniline. Mainly if you're taking nitrobenzene, it reduces to aniline. And then we are talking about the diazotization and the coupling reaction. So let us look into it. So suppose we take ArNO2, that is nitrobenzene. So on reduction in the presence of zinc and HCl, we're going to get ArNH2, that is aniline and water. Correct? So now, obviously, when NaNO2 and HCl, this on reaction is going to give you the HNO2, right? Which is required for diazotization. Now we know that here aniline is obtained. So C6H5NH2 plus HNO2. You're going to get here again in the presence of HCl is present, right? So here we have C6H5N plus Cl minus N2 plus Cl minus. Along with that, there is H2O that is removed off. Now this C6H5N2 here plus Cl minus plus here you're going to take beta naphthol in NaOH, right? So we have beta naphthol in the presence of NaOH. So a coupling reaction takes place. So we have benzene ring, N double bond N. This is from the benzene diazonium chloride. Here we have the beta naphthol part, right? So here, then we have the OH group. So this is nothing but the bright orange red dye. Yes. So this is with respect to the test to detect the presence of nitrohydrocarbon. Now, suppose we get this bright orange red dye. We know that the given compound is a nitrohydrocarbon, but next we need to confirm whether it is a mononitro compound or a dinitro compound, or it may be also aniline. That is another one, which is another class of compound which are present in the group 6. So once you find out that the bright orange red dye is produced, then we know that it is a nitro compound. So we are going to check for whether it is a mononitro or a dinitro compound. If here the bright orange red dye is not produced, then we have to check for anilides. Okay. So now let us look into how to differentiate between a mononitro and a dinitro compound. We need to go for a test called as Janowski reaction. Okay. So How do we perform this test? So mainly, here you're going to take acetone. Okay. So substance, to this you're going to add acetone, and then you're going to add NaOH, and you're going to shake the contents of the test tube. Suppose if a violet color is produced, then we say that a dinitro compound is present. Suppose if there is no violet color that is produced, then we say that the given organic compound is a mononitro compound. So how do we write the reaction for the same? So let us look into how we are going to write. So here a sigma complex is obtained. Okay, so we take the acetone. Okay, CH3CO or CH3, right? Acetone. Now what happens is this can also be written in this way, right? CH2 double bond, again CO minus with CH3. Now, if I'm going to take a dinitro compound, so NO2 and NO2. Now, in the presence of a base, you get here the 6-membered ring. Let me write NO2 and here also NO2, which is already present. Now, here it attacks because of this negative charge. Now, again, this can here and this can attack the carbon, right? So you can get here C, here double bond, and here CH3, right? And here there is the hydrogen. Correct. So now this is how it is formed. Now again, since there is the carbon here is saturated, you can see that hydrogen is there, one more group, and the two bonds are already present in the ring. So here the resonance is lost. So here you're going to get the negative charge. I'm only distributing the negative charge among these different carbon atoms, the 5 carbon atoms. Right. Now, why only in the compound where there is double, where there are 2 nitro groups, only then you can see that the violet color is produced. So this is nothing but this is violet in color, because of which you can say that a dinitro compound is present. Now the reason here is dinitro compound, whenever it is there, there are 2 nitro compounds, there are 2 nitro groups which are attached to the benzene ring, which makes the benzene ring highly electron deficient. So because of which it can stabilize this sigma complex, which is also called as Mesenheimer sigma complex. But if there is only one nitro compound, it does not stabilize this sigma complex that is formed. So because of that, only the compound in which there are 2 electron withdrawing nitro groups, only they give this respective reaction. Okay, the violet color is obtained. So now let us look into the next reaction, that is the test for enzymes. So first of all, you're going to take the substance in a dry test tube, and then to this, you're going to add the alcoholic KOH. Now to this, you're going to add chloroform, right? So this is similar to that of the isocyanide formation, right? So similar reaction. So here, once you add the chloroform, you're going to warm it gently. So when you warm, again, you're going to get the obnoxious smell of isocyanides. So if the isocyanide is formed, then we can say that enzymes are present. So this is how we are going to check for the presence of enzymes. So let us look into the reaction for the same. So RNH COCH3 in the presence of KOH and the chloroform, you're going to get the isocyanide RNC KCl plus potassium carbonate. Okay, so because of the formation of isocyanide, we can say that the obnoxious smell that is obtained. So because of which we can say that the given compound may be aniline. Okay. Yes. So with this, we have come to the end of the functional group analysis. So based on the solubility group that is obtained based on the solubility test, we can decide about the compound belongs to which functional groups. So based on that, we need to check for each of the tests. So we know that in group 1, which are the different compounds that are included, group 2, group 3, till group 6. And based on that, we need to check for each of the groups, each of the compounds. First, we need to check and then we need to confirm about the presence of those compounds. And after that, we are finally coming to the preparation of the derivatives. So this is the final step that we need to conduct in the end, at the end of the organic analysis. Finally, along with the report what you're giving, you need to prepare the derivative for that particular compound, and you have to give the sample of the derivative for the examiner in order to examine and award marks. Okay, so let us come to the last step of the organic analysis, that is preparation of the derivatives. So First of all, we know that there are various compounds that are given to you, which are included in your syllabus. It can be resorcinol, urea, glucose, aniline, all these compounds. So I'll be taking up these important compounds, how to prepare the derivatives for each of these compounds, and what is the structure of the derivative for each of them. So mainly when you're giving the report at the end, you're going to write the structure of the derivative also. So you need to know it very clearly how to write the structure as well as the name of the derivative. So let us start with understanding how to prepare the derivative for these different compounds. So first of all, if the compound given to you is resorcinol, you're going to prepare the bromo derivative. How you're going to do it? You're going to dissolve the compound in water, and then you're going to add saturated bromine water dropwise until a solid separates out. Now, once you get the solid, you're going to filter it and you're going to dry the solid. Now, the derivative that is obtained is the bromo derivative of resorcinol. So how we are going to write the structure for this? So first of all, here we know that in this case, the resorcinol, it has OH group, as well as here it has OH group. Now, whatever the bromo groups are there, it will be present here. Okay, so this is the structure of the bromo derivative for resorcinol. Next, talking about, suppose the compound given to you is urea, you need to prepare the nitrate derivative. So first, you're going to prepare the saturated solution of urea in water. To this, you're going to add concentrated nitric acid until you get a white crystalline solid. So this white crystalline solid, whatever is obtained, you're going to filter the crystals and then you're going to dry the crystal. Now, whatever the derivative that is obtained is nothing but the urea nitrate. So the name of the derivative is urea nitrate. So here the structure is OH. Here we have NH2, NH2. So here, since H is there, it will become plus, and here we have nitrate, NO3 minus, right? Okay, so the name is urea nitrate, right? And this is the structure. So you need to remember the name as well as the structure of the derivative. Next, coming on to glucose. So suppose if the compound given to you is glucose, you have to prepare the oxazone derivative. So first, you need to dissolve the compound in water. We know that glucose is soluble in water. To this, you're going to add phenyl hydrazine as well as glacial acetic acid. You're going to mix the contents well and you're going to heat it on a boiling water bath until you get yellow crystals. Now, this yellow crystals are nothing but the oxazone that is formed. And here, once you get the crystals, you're going to filter the crystals and dry the crystals and keep it for display. Okay, so the name of the derivative that is formed is glucosazone, or it is nothing but the oxazone derivative. So this is the structure of the compound. So let us write it. So here there is carbon. Here we have N, NH. Here there is phenyl ring because you're going to add phenyl hydrazine, right? So for that here, again here double bond, N, NH. Again we have the phenyl ring here. Now the other configuration about the carbons will be the same. So OH, here H, here OH and H, and here we have CH2OH. This is with respect to the glucose, the oxazone that is formed, the oxazone derivative of glucose. So next, if the compound given to you is aniline, then we are going to do the acetyl derivative. So most of the cases, we are not going to prepare this acetyl derivative since it requires these reagents which are vigorously reactive. So because of that, we don't prepare this derivative until and unless it is specifically mentioned that you need to prepare the derivative and show it to the examiner. Okay, so based on the instructions given, you need to prepare the derivative for aniline. So usually we go for acetylation reaction where we are going to get the acetyl derivative of aniline. So very simple, we are going to take the compound, we are going to add a few drops of acetyl chloride and shake it. You get the crystals. So once you get the crystals, you're going to dry the crystal. You're going to filter it and dry it. Okay, so the derivative that is formed is acetanilide, and the structure of the derivative is also very simple. So C6H5, here we have NH, now COCH, because you've added acetyl chloride, right? So you get the acetanilide as the derivative. Next, suppose if the compound given to you is phenol, you're going to prepare the bromo derivative. Again, to the few drops of the compound, you're going to add saturated bromine water dropwise, again until a solid separates out. Once you get the solid, you're going to filter the precipitate and then dry the solid. You're going to get the bromo derivative of phenol. So the structure of the derivative is here in this way. So we know that OH is present. This is phenol. So we have bromine as well as here bromine. So tri-substituted bromine is obtained, so which is nothing but the bromo derivative of phenol. Suppose if the compound given to you is salicylic acid, then we are going to do the acetyl derivative. So here also, based on the instructions, you need to prepare this derivative. So, but you need to remember the structure as well as the procedure that has to be carried out in order to prepare the acetyl derivative. Okay. And based on the conditions that are present in the laboratory as well as the safety concerns, all of these we need to take into consideration, and then we need to prepare this acetyl derivative. Okay. So first of all, you're going to take the compound in a dry test tube, and to this you're going to add acetyl chloride and 2 drops of concentrated sulfuric acid. Again, you're going to heat it in a water bath for about 5 minutes and then pour the contents of the beaker into the ice cold water along with stirring. So again, you're going to get the crystals. So filter the crystals and dry the crystals. So the derivative obtained is acetyl derivative of salicylic acid. So here we have the compound. So salicylic acid. So COOH group is there, right? Along with that, here, whatever the OH is there, so there the acetylation occurs. So OCOCH3. So you're going to get the acetyl derivative of salicylic acid. Now, suppose if the given compound is benzoic acid, then you're going to prepare the nitro derivative. So to the compound which is taken in a dry test tube, you're going to add concentrated sulfuric acid as well as concentrated HNO3. Both will be taken in 1 ml each. Then you're going to heat the mixture on a boiling water bath, and then you're going to cool the reaction mixture and pour it into ice cold water. After you get the crystals, you're going to filter it and dry the crystals. So the derivative obtained is nitro derivative of benzoic acid. So you're going to write the structure. So here we have benzoic acid, and here in the meta position, we have the nitro group. So next, suppose if benzyl alcohol is given, then you're going to prepare the acid derivative. That is, you're going to get the benzoic acid. Now to the compound, you're going to add NaOH solution, and then you're going to add KMnO4 solution. You're going to boil the contents for about 5 minutes. You're going to cool it, filter the solution, as well as now whatever the filtrate you're getting, you're going to acidify that filtrate with HCl. Now we can see the crystals that are forming. So this we have already seen. The carboxylic acid, it can be filtered out. It can be, the solid can separate out whenever you're going to acidify the solution. So that is how we are going to get the acid, benzoic acid. Now after filtration, you're going to dry the solid. Now whatever the acid derivative you have obtained is nothing but the benzoic acid. So the structure is very simple here. We have the benzene ring with the COOH group that is attached to the ring. Next, suppose if benzaldehyde or acetophenone is given to you, so we are going to prepare the 2,4-dinitrophenyl hydrazone derivative. So to the compound, you're going to add a few drops of 2,4-DNP reagent, and then you're going to shake well. Whatever the precipitate, whatever you're going to get, the crystals that are formed, you're going to filter the precipitate, and then you're going to dry the solid and keep it for inspection. Okay, so let us see how we are going to write it for benzaldehyde, the derivative. So we have here En, here NH. So here 2,4-dinitrophenyl, right? So we have here in the second position nitro group, and again in the fourth position. So 2 here, 3, 4. So NO2, right? So this is with respect to the benzaldehyde. Similarly, for acetophenone, same thing. You're going to prepare 2,4-dinitrophenyl hydrazone derivative. So same procedure. To the compound, you're going to add few drops of 2,4-DNP reagent, and then you're going to shake it well. So whatever the precipitate is obtained, you're going to filter it and dry the solid. You're going to get 2,4-dinitrophenyl hydrazone derivative. So let us try to write it for acetophenone. So acetophenone is C6H5CO. There is one CH3 group that is present here. So now there will be a double bond here. Again, the other structure remains the same, right? So in the second position, there is nitro group, and in the fourth position, there is one more nitro group, right? So suppose now the given compound is ethyl benzoate. So you are going to prepare the acid derivative. So to the compound, you're going to add NaOH solution. Ethyl benzoate is an ester. So you're going to add NaOH. Now you're going to boil it for 5 minutes and cool it. Now acidify with concentrated HCl. Now we know that the acid will be precipitated out. So the solid which is separating out is nothing but the acid. So you're going to filter it and then dry the solid. So here you're going to get the acid derivative. Now ethyl benzoate, that means the acid part of this particular ester is nothing but the benzoic acid. So here by this reaction, you're going to get the acid derivative. So COOH, which is nothing but the benzoic acid that is obtained. So this we have already discussed in detail. So when you're adding NaOH, the hydrolysis of the ester takes place, and then of course on acidification you're going to get the acid, right? When you add NaOH, you're going to get the sodium salt of benzoic acid. So on acidification of the reaction mixture by HCl, you're going to get the benzoic acid which separates out as a solid. So next, coming on to chlorobenzene, if this is the compound that is given to you, now you're going to prepare the nitro derivative. So to the compound which is taken in a dry test tube, you're going to add concentrated H2SO4 as well as concentrated HNO3. Now you're going to heat the mixture on a boiling water bath for around 10 minutes. Then you're going to cool the reaction mixture by, again, what we are going to do is we are going to pour the reaction mixture into the ice cold water after cooling. Now you can see that yellow crystals are formed. Same thing. You're going to filter the crystals and you're going to dry the crystals. Whatever the derivative that is obtained is a nitro derivative of chlorobenzene. Now it is very clear that chloro group, it directs the incoming group to the ortho position. So we have chlorobenzene, which gives the nitro group in the ortho position. Suppose you have been given biphenyl, so you're going to prepare the acid derivative. So you're going to take the substance in a dry test tube, and then you're going to add a few drops of chromic acid. Mainly that is a mixture of potassium dichromate crystals as well as concentrated H2SO4. Now you're going to shake the contents well and you're going to add water. So you're going to see that the solid is separated out. So you're going to filter it and then dry the solid. So here again, you're going to get the acid derivative, which is nothing but the benzoic acid. So this is the structure of the derivative here. Next, suppose if benzamide is the compound that is given to you, again, you're going to prepare the acid derivative. So to the compound, you're going to add NaOH solution. You're going to boil it for 5 minutes. Now you're going to cool the reaction mixture and acidify with concentrated HCl. So again, whatever the benzoic acid is crystallized out or separated out, you're going to filter the solid as well as you're going to dry the solid and keep it for inspection. So here also the derivative that is obtained is benzoic acid. Right? So next, coming on to, suppose if nitrobenzene is the compound that is given to you, you're going to prepare the dinitro derivative. Okay, so nitro derivative of nitrobenzene is prepared as a derivative. So you're going to perform the nitration test. So take the compound in a dry test tube. You're going to add the nitrating mixture, 1 ml of concentrated H2SO4 and 1 ml of concentrated HNO3. And then you're going to heat the mixture in a boiling water bath for 10 minutes and then cool it, and you're going to pour it into the ice cold water. Now, whatever the yellow crystals you're going to get, you're going to filter it and you're going to dry the crystals. Whatever the derivative obtained is the nitro derivative of nitrobenzene. So you're going to see that here already there is a nitro group. Now in the meta position, you're going to get another nitro group that is attached to the ring. Right. So next is meta-dinitrobenzene. If this particular compound was given to you, then how you're going to prepare the derivative. So you're going to dissolve the compound in benzene in a dry test tube, and then you're going to add naphthalene. Now you're going to warm it and shake it for a few minutes. Again, you get a solid. So whatever the solid is obtained, you're going to filter it and then dry the solid and keep it for inspection. So the derivative obtained is a naphthalene adduct of meta-dinitrobenzene. So just an adduct is formed. So dinitrobenzene, meta-dinitrobenzene, it forms the adduct with the naphthalene. Okay, so this is the structure of the derivative. So this is with respect to preparation of derivatives, how you need to prepare and also how you need to write the structure of the various derivatives that are obtained. Now, finally, the very important part, once you complete all the analysis, all the steps that are involved in the organic analysis, you need to report whatever you have, especially your findings, whatever you have seen in whatever the observations that you have seen in the various steps of the analysis. So this is how you need to prepare the table. So first of all, you need to write the name of the compound. So suppose if it is aniline or whatever it is, benzoic acid, salicylic acid, anything, you're going to write it here. You're going to write the melting point or the boiling point based on the physical state. So suppose if it is a liquid, you're going to write the boiling point. Suppose if it is the solid which is given to you, you're going to write the respective melting point of that particular compound. Then you're going to write the solubility group, whether it is belonging to the first group, second group, third group, based on whatever the solubility group. Now, suppose if it is aniline, which you have got, then obviously here you're going to write group 3. Suppose if it was salicylic acid or benzoic acid, you're going to write it as group 4 and so on. Then you're going to write the functional group. Suppose for aniline, you're going to write NH2. So in this way, okay. Suppose if it was benzaldehyde, CHO will be the functional group and so on. So based on which compound has been given to you, you're going to write the respective functional group under this. Then you're going to write the structure of the compound. So you need to write the structure of that particular compound which is given to you for analysis. Then you're going to write the name of the derivative. So we have seen for certain, for example, we have seen that for aniline, acetanilide is the derivative. So you're going to write the name of the derivative. And also, it is very important to write the structure of the derivative. So this is the report that you need to write at the end of the organic analysis. And along with this, you have to write all the tests, whichever you have performed, along with the observations and the inference, along with the starting preliminary test, solubility test, the Lassigne's test, everything. And the solubility test, you need to write it in the form of a table, and you have to give the report after the solubility test about the compound is soluble in which solvent, as well as it belongs to which group. And also you need to write there the compound may be. So I have explained it in detail. So finally, this is the report that you need to give along with the derivative, especially the solid which you have prepared, the solid derivative, you need to give it for inspection. I hope it is clear. So I hope this video is useful. I have explained the entire organic analysis process, all the different tests that you need to perform based on whichever compound has been given. First, you need to decide it based on the preliminary examination, which gives you a basic idea about what may be the compound. Then you're going for the sodium fusion extract, where you get an idea about the elements that are present. Then the solubility test, which helps you in determining the group to which the compound belongs. And then the functional group analysis, which is very important. You need to write the test as well as the confirmatory test for each of them under the functional group analysis. And finally, the preparation of the derivative. Along with that, the structure of the derivative has to be written, and along with the neat report of whatever has been given to you. Okay, so I hope the video is useful. Thank you so much for watching the video. Subscribe my channel for more such informative chemistry related videos. Thank you.